Okay, I'm very happy to announce Sam Raskin from Yale University. He will tell us about the geometric Langlands conjecture.
Thank you very much for inviting me. I switched to 11. Okay, so this is a joint project with many co-authors. It's Arinkin, Beraldo, Chen, Faergeman, Gaitsgory, Lin, Rozenblyum. It's a series of 5 papers, and co-authorship is complicated. So to say once and for all, the whole project is joint with all of these people, and somehow it's especially joint with Gaitsgory, who's on all the papers. So the main theorem is what's called the geometric Langlands conjecture. And so it says the following. I guess maybe I'll do it quite quickly for a second. So I'm going to work with a field K of characteristic 0. And I'm going to fix x over K smooth projective curve. I'm going to fix G a reductive group, connected reductive with a dual group G check. And then the theorem says the following. So there's the category of D modules on bun G. And then there's, so bun G, it's the moduli stack of all G bundles on this curve. So for instance, when the group is GM, this is roughly the Jacobian. There's a stack key factor of BGM and a Z parameterizing the degree, but it's essentially the Jacobian. And in general, it's some kind of interesting space. And then there's also the space of local systems for the Langlands dual group. So when I say locsys right now, I mean in the DRAM sense. So if I'm talking about GLN, they're vector bundles with connection, and I'm considering the moduli stack of those. The goal is to compare these two objects. And unfortunately, they're not equivalent, but there are two things that one can say. So the first is there's a slight correction to this category, which is called intco nilp. It's a slightly bigger object, and I don't kind of want to get into the definition right now. The first way to say this is that there's a geometric Langlands functor that's an equivalence between D modules on bun G and this intco nilp bun locsys G check. And the second way one can state this is that there's a quotient they call the category of tempered D modules. And this is also going to have an equivalence I call tempered geometric Langlands between this quotient category and this category of quasi-coherent sheaves on this locsys G check. And this tempered thing, I don't want to say the definition. Roughly for PGL2, I quotient by, precisely I quotient by sheaves with constant cohomology in this quotient operation, but in general, it's something slightly technical to say. And yeah, but that's the theorem. And you should think that the assertion that this functor is an equivalence is as difficult as the assertion that this is an equivalence. There's some theory that goes into that. There's some theory that goes into proving that, but practical purposes, you can think of them as roughly equivalent statements.
When you say they have categories in bounded, unbounded?
That's a great question. So it's so this functor has infinite amplitude. This functor actually has finite amplitude, and so I do mean unbounded derived category, and it's kind of essential in some sense on top, and yeah, but there. Maybe let me comment for a moment that there's some variants that I don't quite want to say, so a lot about, so maybe I'll just say very briefly. So so there's a Betty version of this theorem in which I work over the complex numbers and I consider sheaves with nilpotent singular support on bun G. And when I say sheaves here, for instance, when I talk about local systems, that would be a special case of a sheaf with nilpotent singular support. I allow infinite rank local systems. So I really mean sort of representations of type 1. And that these are going to be equivalent to something of very similar nature. So, sorry. The same int code nilp sort of game for the moduli space of Betty local systems. And there's again this picture. The tempered quotient. And the space of quasi-coherent sheaves looks as check Betty. And actually a nice phenomenon is that this functor down here is T exact. So it preserves the T structures. So this is actually an equivalence of abelian categories in the sense where this is given some quotient T structure. And so in that setting, so there's kind of a question, I would say in some sense, there's a question, what do you mean by the geometric Langlands conjecture? And right now there's like 4 things on the board that one could mean, and I could write 4 more in a moment.
And it's all unramified.
It's all unramified, yeah. So for practical purposes, you should think each of these statements is equivalent to any other. You can move from one to the next. And in this sense, you could think of, so if you took this as your statement, you could think of geometric Langlands as an equivalence of abelian categories.
When you say it's T exact, for which T structure on sheaf nope?
So here it's the perverse T structure, and then the statement is this picks up a quotient T structure.
So that's not true on the left?
It's not true on the left, yeah. So
Could you give some hint where the distinction comes?
Could I give some hint where the distinction comes? So for like the group GM, this equivalence is some version of a Fourier-Mukai transform for abelian varieties. And there's just kind of an experimental fact that cohomological shifts occur in that story. So it has, that's an equivalence that has amplitude equal to it has amplitude equal to the dimension of the abelian variety. And so how should I say?
Like this T exactness is kind of related to the fact that automorphic eigensheaves are perverse, right?
Yes.
But then that you're saying somehow that's less true on the left.
Yes. It's less true on the left. So it's something about the kind of families that the way families work in the Betty setting versus the Durham setting. So in some sense, you can have a family of D modules where, well, this is some kind of general feature of the Betty picture. It's related to the fact that, although not the same as the fact that this is much more like an affine scheme than the Durham version. So I would say that's the most elementary statement in that. So, other questions? Yeah, and I'm going to say some separate results. So these are kind of like the categorical statements, but I also want to formulate kind of what's known about Hecke eigensheaves. So I'm just going, there's a certain cohomological shift here I'm going to ignore, but doesn't matter. So take, so let me just say what's known about the structure of Hecke eigensheaves these days. So take sigma to be an irreducible G-check local system, meaning it doesn't admit any reduction to a proper parabolic. And take F sigma in this category of D modules on bun G to this corresponding object. To the delta sheaf at sigma. Under geometric Langlands. So. Under the geometric Langlands, well, call it GLC. So then the following results are known. So the first thing is that F sigma is regular holonomic. Second thing is that M sigma is reverse. So that's, I mean, it follows from this T exactness statement, for instance. The reverse, I mean, reverse, I mean, it's in degree 0 as a complex. This is in degree 0. With respect to the T structure. Third thing is that F sigma is semi-simple as a perverse sheaf. Fourth thing is that actually F sigma, I can write down exactly what it is I can write down its Jordan-Holder series. So it's going to be a direct sum of things I'll call F sigma rho, the dimension of rho, where here rho is going to run over all irreducible representations of the centralizer sigmas. The group of automorphisms of sigma is a local system. And maybe I'll just remind that S sigma mod the center of the group is always finite. And this condition here you should think of as somehow analogous to the phenomenon of L packets in the arithmetic theory. And the fifth thing, which unfortunately at the moment I can only prove if the center of G is connected, is that the characteristic cycle of this F sigma is exactly the nilpotent cone. So the nilpotent cone is the inverse image of 0 under the Hitchin map. And so you don't have to. I'm not going to say what it is in detail, but it's just to say that the characteristic cycle is known and given by some explicit formula. Yeah. So that's what we know in modern era. Or that's what we know today about the shape of these Hecke eigensheaves. So yeah, so this tells you, for instance, like any perverse sheaf, at the generic point of your stack, it's going to be a local system. And this tells you, for instance, what the rank of that local system is. Okay, any questions before I go on?
Can you give an example of what is S sigma? You have trouble picturing what it means.
Like, yeah, somehow it.
Automorphism in what sense?
Yeah, I mean automorphism as a point in the stack. So if you think of sigma as a map from pi1 of the curve to G check, this is everything that centralizes the image of that automorphism. So if the group were GLN, then this would just be a singleton.
Yes.
Famously, but in general, what happens for general reductive groups is it's finite. So yeah. So for instance, like if you take the standard representation of PGL of the symmetric group on 3 letters, and you consider that as a representation into PGL2, it has a slightly larger centralizer than has a Z-mod2 centralizing it. Other questions? Great, so those are the main theorems. And so now what I want to do is somehow, and I guess I'm not really going to talk about this stuff about the structure of Hecke eigensheaves, but one thing that I think personally is slightly remarkable is it's related to a lot of the tools that we use in setting this up. And also some of these theorems are, oh, I should have put attributions also. I'll do that in a second. But one thing that's slightly remarkable to me is that some of these results are really proved using these equivalences of categories, which don't seem to tell you very much at all about the nature of the questions that are occurring on the board. So that's just one kind of comment that I at least like. So attributions, so this is from a joint series of papers with Arinkin, Gaitsgory, Kazdan, Rozenblyum, myself, and Faergeman. I guess Hecke and I went in the other order there. This is a joint project with Joachim Faergeman. This is also due to that. This is kind of that plus the geometric Langlands conjecture. And this theorem is something new, which is in one of the papers with Dennis. Yeah. Oh, and actually this also was. And we were able to prove these unconditionally when this group was trivial within GLC.
Give reference also instead of authors.
Instead of authors. Well, it's essentially unique. So yeah, so here, this paper, this FR under. Okay, can I defer on this? So I think tomorrow or either tomorrow or Wednesday, the first in our series of papers will occur on the archive. There's a section at the end that says all of these results, and each of these has good references. So so maybe just for the sake of time. Yeah. Okay. Other questions? So what I want to do is say somehow overall, kind of the strategy of how we'll do this. So what I'm going to focus on is going to be kind of, this main theorem, stating that there's this geometric Langlands equivalence. And I want to try to say, I want to give some kind of overview of what we do in order to prove this theorem as best I can in the time allotted. Also, there's a fact about this field, which is that, it's been going on for decades and not everything's always percolated. So there's certain things you'll kind of maybe have to take on faith. And it's 5 papers being summarized in an hour. So overall, the goal is the following. So the first thing we'll do is we'll construct this Functor LG. The second thing we'll do is study structural features of this LG. And then the fourth thing we'll do is a bunch of tricks to deduce the theorem. Maybe I can't quite explain all the tricks, but I'll explain my favorite of them, just the generic trick. Yeah, and I should say the random tricks somehow that occur here. You can imagine that there are more conceptual things a person can do. We write about this in the beginning of our paper, and it would be really great to have a better understanding of that part of the story.
So where in this thing will something like the construction of a Hecke eigensheaf happen?
I guess in this construction is LG. Let me return to that question later. I'll tell you what the Hecke eigensheaf is, but it's not a super satisfying answer, which is part of why I find this. I mean, there's a formula for what the Hecke eigensheaf is, and it makes none of what I said clear. So,
Soon into the Ham world, what you are telling me.
Yeah, so now everything is in the Jerome world. That's correct. Okay, so the first thing I want to do is construct this functor LG. And so I don't know if maybe this isn't meaningful to this round or something, but what I want to say is that this can be thought of as some kind of souped up version of circle theory. So I want to do something like what happens in circle theory to construct this functor. So circle studied category O in combinatorial terms. And the way that worked is that there was a certain particular object that was really important called the big projective object. There's a second thing, which is that the category has kind of in some sense, a big center. And then there's some homological algebra tricks that you do at the end of the day, which are a little funny, and it'll be exactly the same progression here. So I'm going to name a particular object for you, like the big projective. I'll say that there's somehow a big center, in some sense, and then we'll do homological algebra tricks. So the first thing I'm doing is this construction of the functor. And so there's kind of a certain key functor, which is called the functor of first or zeroth, Whittaker coefficient. And it goes from this category of D modules on bun G, the category of vector spaces. And so let me just say how it works. So let me just assume my group is PGL2 for simplicity. General case is not very different. So there's bun G. There's going to be a kind of twisted version of bun N. N is the radical of the Berel. And my twisted version of the Berel, I'm going to think of as parameterizing extensions. This. So if I had O and O here, then zeros. If I had O and O here, this would just be bun N, but there's an omega twist, so put the omega in. This maps to H1 of omega 1, taking the class of an extension. Let me call this projection P, and of course this is A1. And by definition, the coefficient of sheaf F is going to be given as follows. So I take the cohomology, so this just means complex of Jerome cohomology of the pullback of my sheaf, this bun N, twisted bun N, and then I'll tensor it with the pullback of the exponential sheaf along this character psi. This is going to be hung from a certain object of the Poincare sheaf, my F, where this Poincare sheaf is just rigged, so this formula is true. So it's like psi upper star of this exponential. Maybe there's a twist by something, and then do this P lower sheaf. Probably shift by plus or minus 2. Minus 2, please. Okay, ignore cohomological shifts. So this is kind of some kind of basic object of study in the story. So it's analogous to this big projective. This coefficient functor is analogous to Sergal's functor V in this sense. The key thing that you should think is that, okay, first of all, if this is GM, then I'm taking the skyscraper sheaf at the origin inside of bun GM, which is some kind of, you think, abelian group. And what we're doing is some kind of Fourier theory. So this Poincare sheaf in general, it's playing the role of kind of like the delta at 0 in usual Fourier theory. So this is something that you should think kind of a main part of our job is to prove that it's kind of like white noise. It's a perfect superposition of all of the possible modes. That's like a preview of something that has happened. Did I break something? Just do that. Okay.
What is this? What is on the, no, before the top. Next one.
What's the next one? Here's what you do. You take your sheaf F, you pull it back to the spun n omega, then you also pull back the exponential D module. You tensor the two of them together, and then you take cohomology.
Ah.
So
It's
this
a gamma.
C Durham means the cochain complex of Durham
Ah.
cohomology.
Oh, okay.
Yes, so it's like H Durham, but C. Okay, so that was the first thing. So it's like when you do Fourier theory, yeah, again, there's a distinguished role played by the skyscraper sheaf at the origin, or by the delta function at the origin, and this is the analogous object. The second thing is going to be about symmetries of this category. So the statement is that in some sense, there's this category kind of has a large, it's not center, it's not the right word, but it has a large collection of commuting endofunctors. So whenever you have a point x and x, geometric Satake, so I remind this is the curve. This gives rise to an action of rec G check on this category of D modules on bun D. And so there's a theorem, Gaitsgory-Drinfeld, which I'm not going to state any more precisely than it will makes me to, but so the assertion is that there exists a unique action called the spectral action, quasi-co-loxis G check acting on this D at bun G. That is compatible with a souped up version of the Hecke action. So souped up version of the Hecke action means I can allow x to vary. And I also allow multisets of points. So if you had two distinct points, then you get Hecke actions at each of those points. So the Hecke action, the distinct points commute, and somehow as you let one point come down to the other point, the action here and the action here sort of limits to the action of the tensor product of two representations. And if you say a bunch of formal words to make that very precise, then what they prove is that there exists a unique action of quasi-co-loxis G check, which is compatible in the natural sense with this Hecke action. So you can think of this as
Compatible means with this kind of compatibility.
so it means the following. So if you take a point in the curve, say, so this will map you from local systems on X to local systems on, let me say, the formal neighborhood of the point, just for my own psychology, which is a copy of the classifying stack of this point. So if you had an action like this, you could take a representation as a sheaf here, form a vector bundle on loxis G check, and then act on D of bun G by this action, and you get some endofunctor. And that should be my Hecke action. And again, you should say these words with moving points and things, yeah. So this is kind of the statement, this is the statement of reciprocity in some sense in this world. So it's saying that the Hecke eigenvalues of eigensheaves, for instance, are actually, well, the Hecke eigenvalues that you see in D of bun G actually have to do with local systems for the Langlands group.
And local system always mean reducible local system.
It does not always mean reducible, but this will be an important point, yeah.
Oh, Does not or does not?
Does not mean
Does
irreducible.
not.
Yeah, so when I talked about eigensheaves, those were for irreducible local systems, but now it's arbitrary local systems. Something remarkable is that our strategy, it uses reducible local systems to prove something about irreducible local systems. Yeah, so now the theorem about the existence of the functor says the following. The first thing is that there exists a unique, so I'm going to kind of collect a few things, and not all of them are really assertions, but first thing is that there exists this unique functor, I'll call LG temp. Goes from the d of on G to quasi-co locus G-cap. That's linear, so it's a map of quasi-co locus check module categories. So that is, and that's normalized in the following way. So if you take this, well, maybe I'll do the diagram, would be nicer. So what I want is that this, when you take d of on G, you map it via this functor, this tempered geometric Langlands functor. And then you map this down to vector spaces and global sections. This is supposed to be my functor of taking the Whittaker coefficients. And so for people who know Whittaker coefficients, this is some, this records kind of two things for a number theorist. So first, it encodes all of the Whittaker coefficients of a automorphic D module. And it also kind of, the fact that it maps here kind of encodes the existence of reciprocity laws between those automorphic D modules. And I want to say this it's a tautology from the theorem that they wrote. It's some very formal kind of thing. So it didn't have anything to do with this being this functor. It could have been any functor. It didn't have anything to do with this being this category. It could have been any category. It didn't have to do with locus G check being anything. It just had to be some nice stack that acted on your category. So I'll just say this is a formal the spectral action. So the second thing is that this LG temp has finite amplitude, as we discussed before. And then the third thing is that what are called compact objects. So sort of, let me just say, I work with big categories with direct sums. Maybe you work with small categories that don't have infinite direct sums. And if you work with a small category, I would call that the category of compact objects. And you and I, we can talk to each other. I have more functors than you have, but we can go from my category to your category algorithmically, and your category to my category. So these compact objects are bounded below. So these are compact objects in D of 1G. These are bounded below. So this is some very minor assertion that is only an assertion because of the non-quasi-compactness of 1G. And the last thing, which is maybe the most important point, but also is formal from A, B, and C.
Sorry, C does not invoke the functor.
It does not invoke the functor. That's correct. D invokes the functor. Yeah. So I'm going to take this D at 1G and form that same commutative diagram. And the assertion is that there exists this unique y. Fitting into the diagram as before. Let me just, for brevity, I'll add this there. So, get there. That's right on LG temp. And this is such that whenever I apply my functor LG to a compact object, this is bounded below. So in other words, to tell you this functor LG, I just need to tell you what it does on compacts. That's part of our language between big categories and small categories. And let me tell you what it does. Okay, there's all of this int code. Nope, I didn't really say very much about it. The key thing to know about it is that the bounded below derived category of anything called intco is the same as the bounded below derived category of quasi-co. So they're just the same bounded below derived category, but the unbounded place is where interesting things happen. So if I want to tell you LG of some compact object, which is all I have to do according to our, treaty between big categories and small categories, I have to tell you where it maps as an object here. But by C, that object was bounded below. By B, it maps to something bounded below. And so I'm just going to require that it map, like the bounded below category objects here are the same as the bounded below objects here. So that just tells me where it had to go.
But you also have this importance condition. Is it also?
The same thing. It doesn't matter. Yeah, I could have built the functor to intco or intco nope or anything. For it to be an equivalence, it has to be this intco. But the same construction would have worked without the null. So this theory, in some sense, it produces a bunch of categories that interpolate and all have the same bounded categories. So there's something remarkable, which is like, maybe I should have said before, this Whittaker coefficient operation. It's like taking a modular form to like A1 of the modular form. You can think of this functor somehow encoding all of the ANs of your modular form for n greater than or equal to 1. The failure of this to be an equivalence, for instance, is related to the fact that like there's a constant function that has vanishing ANs for n greater than or equal to 1. And but what this is saying is that actually somehow categorically you can ignore, you don't need to worry about the fact that you missed the constant term of your modular form. You actually can recover it from the non-constant terms by categorical magic, which is a nice thing. So one of the key things is that Whittaker coefficients control almost everything, and you can sort of build off of them in practice to get information about things that have actually vanishing Whittaker coefficients.
I think I understand what you mean by A1 for VL2, but in higher rank, there is the Borel with an additive character of the unipotent radical.
Yes, and there's this n that goes in there. Yeah. So that's what I would do in this case, is some of our bunch of characters.
Oh, and yes, we have a similar twisting to. Yes, for VLN, what replace this?
This thing.
Omega, which you have.
Okay, so let me say for B. So I fixed the square root secretly this morning before I brushed my teeth, and so bun n. You can think of it as B bundles whose induced T bundle is trivial. So bun n omega are B bundles whose induced T bundle is row check of omega, aka 2 row check of the square root of omega. And then I'm summing over simple roots, so it'll map to these spaces for GA.
Sorry, Sam, can you give an example of where C fails for other stacks?
Where it's super general.
Okay.
Yeah, it doesn't really have to do with bungee.
Okay.
The thing it has to do with bungee is like, it's because of non-quasi compactness, it's not obvious that bungee actually, D modules on bungee is compactly generated. It's a theorem of Drinfeld and Gaitsgory. They give a general geometric mechanism. The only example of a thing like that I really know is bungee. And so the fact that is an issue at all, it's sort of that bungee is a little bit of a weird space, and this non-quasi compactness of bungee, and the way it's resolved is the way somehow many such problems are resolved. So it's something very, very general. Other questions? But the issue is the compacts are J lower shrieks from some quasi-compact open, and you have to bound how bad that J lower shriek can get on the left. So that's the issue. Okay. So now let me say a little bit more kind of setup for the moment. So that was the construction of the functor. The next thing I want to do is I'll say the following. So let me be in the setting of this kind of tempered quotient. didn't quite say what it is, but I hope you'll excuse me for it. So there's this thing, LG10, but a little bit being vague about what the, or inconsistent about what the domain is. You okay with this? So this has a left adjoint, sorry, I drew the diagram the wrong way, which sends the structure sheaf to this object I called before the Poincare sheaf. So, the adjunction still exists. So this is the left adjoint and this is the right adjoint functor. Both of these functors are linear. And so, yeah, and I guess one of the key points is a theorem, and maybe I don't like it, but same Faergeman and Raskin, and it's from 22, our paper. And it says that this functor LG temp is conservative. So it sends no non-zero objects to zero. If you go to zero, if all of your Fourier coefficients are zero, then you're zero up to this difference between tempered and non-tempered things. This was known previously for GLN, I'll just say the proof for GLN uses the Mirabolic group. It's in some sense, it's copy pasting the proof of multiplicity one for, or at least some version of this theorem, I should say, was known before for GLN. And you should think that it's kind of copy pasting the proof of multiplicity one for automorphic forms for GLN. And it's not, if you've thought about these things before, it's a non-trivial result for groups besides GLN. And in some sense, this is kind of the theorem that got stuff started. I think it's in some sense, there's nicer geometry going on there, but it's not what I'm going to explain today. So what you need to show when you have the situation of a conservative functor that has an adjoint, so that means that, so what I'm going to do is I'm going to introduce an object I'm going to call AG, which is the quasi-coherent sheaf on Localization G check. It's going to be by definition this LG temp applied to the Poincare sheaf. So you should think of it as encoding somehow the Fourier modes of this delta at one of this Poincare sheaf. So this is the definition. It's actually an algebra, just by general stuff about adjoint functors. And what you're going to get for free from what's called the Bar-Beck theorem is that this D modules on bungee temp is going to be equivalent to the category of modules over this AG. So you should think this AG controls the multiplicities of Hecke eigensheaves. So our goal, in other words, is to show that the map from O on locus to this AG is an isomorphism. So this is the unit map for the algebra structure. And so everything reduces to understanding this AG, aka the Fourier, the Whittaker coefficients of the Poincare sheaf itself.
Does the fact that category is modules from AG depend on this conservative?
That just uses the conservativity, exactly, yeah. So what you should think is 2022, it was such a long time ago, who remembers, but that got some part of proving that it's an equivalence off the ground, and now all we worry about is the stuff after that.
So global sections of AG are like endomorphisms of the Poincare sheaf?
Yes, and that'll be relevant later. That's correct. And somehow, yeah, and you could also kind of tensor by one of those vector bundles on locus I said before, and that'll have to do with other Fourier coefficients of the Poincare sheaf. And in some sense, if you test enough of those, you know what this AG object is. But yeah, the other thing is if you take the fiber of AG as some local system sigma, modules over that are Hecke eigensheaves with that fixed local system as the eigenvalue. Okay, so now I'm going to start doing Kac-Moody input. So This is used to prove structural features of.
Wait, Sam, sorry, let's repeat that. You said, so if I'm worried, when I'm worried that I'm not getting every local system from a Hecke eigensheaf, that would correspond to the support of AG missing some points.
Correct.
Okay.
And if you were concerned that there were two Hecke eigensheaves, that would correspond to this AG sigma looking like 2 by 2 matrices. Actually, or maybe better is like K times K. Yeah. So, and again, that will be super important in a bit. So this is used to prove, again, structural features of. So maybe just very briefly for people who don't know, so there's something called the Kac-Moody algebra at critical level. It was studied in the 80s by Faergeman and Frankel. And then Beilinson-Drinfeld used it to prove some nice theorems about Hecke eigensheaves in the 90s. And we're going to use kind of the same tool in order to study D modules on Bun G. So it's a way of producing certain nice D modules kind of by generators and relations that happen to interact very well with all the things we do in geometric Langlands. And almost everything is obtained by Kac-Moody localization. And so this is a great tool. So, I'm going to write down kind of this first kind of commutative diagram. So there's going to be this Cauchy-Lustig category. So first theorem that we're using in order to do this is there's this Cauchy-Lustig category. It's going to be equivalent to this info of what are called monodromy-free operas on a formal disk. This is the functor of Kac-Moody localization that I just mentioned. Yeah, this is called the FLE. This is my Langlands functor, I guess tempered. And this is going to be this category of quasi-coherent sheaves on low cis feature. And this is some kind of local to local construction. This goes by the name of Functor star Spectral. So it's you can think of it as an analog for G-check and local systems of the construction of Functor sheaf.
So you have 200 pounds on the curve?
And what?
If 200.
This is a great question. Yeah. So first, it's kind of similar to before. So first, I interpret this diagram with the point chosen, and then I interpret the thing as making sense for a moving point. And this will be a category that allows moving points. So for instance, objects supported at a point, but also such objects tensored sort of by a D module. I also allow multi-points here, and then I interpret the theorems in that sense. So kind of properly, these are factorization categories.
What does FLE stand for? Sorry.
Fundamental local equivalence. So it's just notation for this, but there's some general yoga of what's called quantum geometric Langlands, and this kind of thing is supposed to deform at all levels, or is proved these days probably to deform to almost every
It's an old result, or what's needed for you is.
So the version at a point, like again, the expression was known in 2005 or 6, 7 due to Frankel and Gaitsgory, and the upgraded version that allows the moving points. It's sort of a key part of a long paper that we've just put online. So it's one part of it. So you should think there are additional technical complications that come up, which are like non-trivial to get over, but kind of the tools, the kind of categorical tools that have developed over the last 10 years or something, let you handle this without too much additional difficulty. And we do really somehow do need the version with moving points, like, but that's the answer. So basically, you should think there's some representation theory that goes in here. It's older kinds of stuff, and then we give a souped up version of this kind of mono language that has additional technical things, but it's not for the person just trying to learn what the stuff, how the stuff works. I would say learn the pointwise version. Don't worry about the moving points version, first approximation. So this is kind of the thing. So what this says is we can localize D modules. We can start with these Kac-Moody representations at critical level. We can form D modules on Bun G out of them. What do those look like? One example is the sheaf of differential operators. Another is their sort of favorite vector bundles on Bun G. So if you take a point in Bun G, a point in the curve, you get a map from Bun G to like BG. And so you can take a representation of G and then turn that into a vector bundle on Bun G and induce that up to a D module. So that would be another kind of example. And basically everything like this is moving points versions of that example. And what we're saying is that you can compute the Whittaker coefficients of those localized D modules in some kind of G-check terms, some local terms if you want. Namely, you apply this FLE and then you do, which is a kind of local version of this LG temp, and then you do this local to global procedure. And the proof of the theorem, it's a mix of things, but roughly speaking, the proof is chiral algebra theory plus, plus its FLE. And it's long essentially because the paper about this is long only for the reason that what we needed from chiral algebra theory wasn't well documented.
This what supplies essentially large class of objects.
That you can compute things on. That's exactly correct. Yep. So the first application of that. Oh, okay, great. So the first application of this says the following. So it's the Eisenstein compatibility. So this is one. And it says the following. So if you take D modules on Bun G, so I'm going to choose Levy, and I have similar data for the dual group. So I can take D modules on Bun G. I can map it to Bun M by what we call the constant term functor. That's pull back to Bun P, push forward to Bun M. And now this you can map via LG to this int code nope. This is going to be what we call the spectral constant term. It's the same construction, just with these spaces of local systems and G check, P check, and M check. And this will produce actually objects of, well, I rig it to produce objects here. This is going to be, oops, LM. And the assertion is that this diagram commutes. Write it like that. And here's the idea of the proof. So we calculate everything on Kac-Moody localized objects. So you take a Kac-Moody localized object in D of Bun G. That gives you a formula for computing LG of it in some kind of local terms. And then we compute constant terms of that. And that turns out, now by the same mechanism as in here, that turns out to have a local expression. So what that means is you start with your representation in KLG, you do some stuff to it, and but somehow working purely locally on the curve. And then you do some globalization procedure. So that, yeah.
Can you tell what is this bottom line?
Yes, it's pull back to loxis P check, and then push forward to loxis M check.
So, sorry, why do you write that the map from P to G is surjective? That's maybe.
Oops, that's sorry. Yeah. So roughly speaking, the idea is we calculate everything in sight on these Kac-Moody localized guys, and that gives it to you. And let me just say kind of for us what that means. So you can apply induction to assume that you know geometric Langlands for every levy besides G itself. And so what that's going to tell us is that this map I was talking about before from O to AG, that this is an isomorphism on the locus of reducible local systems. I feel like I have to put reducible, whereas you think it's reduced there. Yeah. So.
Do you mean some pullback is another option?
Yeah, I mean that the restriction, yeah, exactly, that the restriction to locus reducible is isomorphism. Or you could say the formal neighborhood of locus reducible, so both, that's kind of the restriction functor is conservative from formal neighborhood. For me, things on the formal neighborhood that like torsion trees. So it's both, not spec. So the second application says that if you have an irreducible local system, so this is what we call ambidexterity, which will be for, it's a weird name, but so if you fix some irreducible local system, so the irreducibility is kind of important here. It's definitely important. So AG irreducible, I mean the restriction of AG to, actually no, I'll just put AG sigma, do it. That this AG sigma has a perfect pairing with homology. So it's, I'm doing my C like before, but this just means homology of slightly weird space. And again, has to do with these operators that people aren't gonna necessarily know unless they do know. So it's can be all operators on X, monodromy free, on this sigma. So these monodromy free operators, maybe I'll just say the nature of it. Well, for GLN, for instance, this is like I fixed a cyclic vector at the generic point of my curve in sigma. It's a vector bundle of connection. So it's a cyclic vector at the generic point. And we prove that there exists a perfect pairing. And this is somehow a perfect pairing between an algebra and a coalgebra. And so this implies lots of great stuff for us. Yeah, I guess we proved that, and we also proved something else, which is more related to this ambidexterity, which is that this, as a vector space, is actually self-dual. So two kind of related statements, and why they're related, that might not be totally obvious. But for us, the upshot is going to be the following. So if you think about homology of a space as a coalgebra, well, it's just the dual to cohomology, which is commutative. Cohomology is also in degrees greater than or equal to 0. So the only way it can be self-dual is if it's purely in degree 0. And so that's going to imply that this AG, like somehow over the irreducible locus, that this is commutative. What's called, well, I'm going to say anti-tals. Over O, and in fact, finite health. The structure sheaf of locus reducible. And the reason it's atal is because the fibers are reduced. All of its fibers look like homology of some space. In fact, it's H0 of that space. That's the only thing that this allows it to be. Yeah.
Right, so you get finiteness?
Because it's self-dual. Otherwise, you get into trouble as a complex. So really what I mean is AG is isomorphic to, like, I should have said it better with the moving point. So AG irreducible is isomorphic to its own dual. So it's not just at the level of points. And it's essentially the same idea. So except this functor is almost surjective. And what you can say is that it's really surjective onto the cuspidal category. And so then you could just try to take this Poincare sheaf and see what is it, like, how do you compute its image under this equivalence? And what you'll see is like you write it as localization of something. In fact, the functor has an adjoint then, so you know what to write as localization of. You compute it using this diagram and you get this answer. So that's a short explanation of what's happening, but that's the idea of the calculation. And that's why operas are coming into the story. So one upshot is that if you know the contractibility of the space of opera structures on your irreducible sigma, then you know geometric Langlands. It's an equivalent assertion after this point. And so now I'm going to do some kind of tricks. So, this is the last bit of the talk. So the tricks are the following. So first, I'm going to make some assumptions. So the genus is going to be at least 2. I'm going to assume that my G is an adjoint group. And I'm going to assume that I'm not in the specific case of PGL2 and 2. So this, for me, it's one of my favorite features. But this particular argument doesn't work in that case. So low genus cases we treat by different means. Let me just say, for instance, just if your group was PGLN, I said an opera structure is a cyclic vector at the generic point. So you can think a cyclic vector for an irreducible local system, that's just another name for a vector. And so it's just like essentially a line in some in the generic, like in the vector bundle restricted to its generic point. So it's some kind of huge infinite dimensional projective space, and those are, or sorry, I should say it's the vector space minus 0. It's a huge, huge space, and so that's intractable. So that lets you do PGLN very directly. And genus 1 and 0, we do it separately. So again, what we have is this kind of multiplicity problem. So we now have this AG. We think about its fiber at an irreducible local system. That's going to be some basically product of copies of K. I assume K is algebraically closed. And I'm trying to show that there's only one K that occurs. There's not 0, there's not 7, there's exactly 1. And so this is going to be something that kind of integrates over the whole moduli space of local systems. So, the main input is a very simple calculation, which says that the global sections of this AG, so actually I did the exercise before, so this endomorphisms of this Poincare sheaf. And you can see that under these assumptions that the genus is at least 2 and the group is adjoint, this is irrelevant, but these are just scalars. So the way this is going to work is that you have this fun n omega mod t. There's going to be an open where the character is non-zero. And this is going to map to fun G. And so this is going to be locally closed under the assumption that, I should say, okay, first of all, the Poincare sheaf will be obtained by first star extending and then shriek pushing forward. So here, star extend, and then I shriek push forward. So this is some kind of just general calculation with exponential sheaves, very tautological. And then what you're going to do is you're going to take this locally, so this is locally closed when G is adjoint and the genus is at least 2. So that push forward is fully faithful. This is certainly a fully faithful push forward. And this guy is essentially a affine space. In fact, it's like it's a unipotent German over one. So it's great. Nothing to do. Yeah, and that's using the figure adjoint also. Actually, this is at least 2. So the idea is that this is telling me this is somehow ruling out that the multiplicities are too big or too small. So it's some kind of key input. It says that these global sections of AG, they're just scalars. One comment is that therefore what I'm doing, it's very particular to the theorem setting. So like there was this Kac-Moody localization, and in some sense, that's very Durami. Of course, it's extremely Durami, but it's not as Durami as this in my mind. Because I'm going to use the fact that these endomorphisms are very small, which corresponds to the fact that there are very few functions on the, very few algebraic functions on the moduli stack of G-check local systems. And so this kind of statement is just not true in, for instance, the Betty setting. Those endomorphisms are quite large for the analog of Poincare sheaf. Okay, so that's my my main thing. So first we prove a probably this was known, but I don't know anything. So we prove that under these assumptions, and now it really matters, that the genus is not 2 and the group PGL2, but this is simply connected. And so therefore, this AG irreducible is just going to be O on this locus, direct sum n minus n times. So that's just what simple connectivity gives you. And my goal is to show that n is equal to 1. Because let me just remind, like I'm supposed to show a particular map as an isomorphism, but it's a map of algebras. And if you think about the fibers at every point, like if you know the fibers are one-dimensional, a map of one-dimensional algebras is an isomorphism. Everything's unitable. So I need to show that this global sections is, sorry, I need to show that this n is equal to 1. So the next thing that we show is that actually, if you take the derived global sections of this AG, and then you take the not derived version. So we just said this is just scalars. So I don't really need to write H0, but
I'm confused.
Yeah.
Was AG not just a cross-variant sheaf? I mean, algebra?
Yeah.
Yeah, but so why this being simply connected implies it's free?
so it was because of this ambidexterity I said before. So I said it's commutative and finite H-Hall.
Oh, sure, yes, okay. Yeah, sorry.
No, I didn't say that very clearly. So the assertion is that this AG irreducible, it actually has the same global sections at the not derived level as AG. Emphasize this as scalars. And here the idea is that we have the following kind of exact triangle. So it's J lower star of this AG irreducible. And then here you're going to have some kind of local cohomology of AG, which is, I read it as I hat upper shriek, no reasons. But this, and I is the embedding of reducible local systems. But this object, we know what it is. It's going to be the same as I upper shriek of O. And this is going to be in degrees greater than or equal to 2. The idea being that that these reducible local systems, so this I upper shriek of O, we have some LCI stack essentially in this setting, so that's some kind of known feature. So this I upper shriek of O, it's up to twists by line bundles, it's the same as I upper shriek of, well, and shifts, it's the same as I upper shriek of omega. So you can just compute very explicitly what it is, and it'll be really in degrees greater than or equal to, I should say, the codimension of reducible local systems, which we show is greater than or equal to 2, again, under our funny assumptions. And once you know that, then for free, you get this assertion above. But now the idea is, well, I guess I'll just repeat what I just put. So K is this H0 of global sections of AG by what we said before, which was global sections. Where is it?
We wrote this I upper shriek of AG is equal to I upper shriek O. Is this induction?
This is the induction, exactly. Yep. So this is the same as the irreducible version. This is the same as H0 of global sections of O direct sum n times. And this has dimension greater than or equal to n. And so we see that n has to be 1. So that ends the argument. So then, yeah, there's low genus cases, there's the center, there's all this stuff to worry about, but that's the main thing. So, yeah. Thank you very much.
Any questions for the speakers?
There's a characteristic P version of the story by Spencer Cumming and Beraldo. Does it fit?
Is it what?
It's a characteristic P version of the story by Beraldo and Cumming. Does it fit in this?
Yes, but so what they do is it's very generic on the space of local system. So I mean, I guess there's a simpler question. So what Bezirkovnikov and Braverman do is somehow okay. Another thing which is known is, for instance, for GM, the cotangent bundle of like you can think about D modules on bun G as something like quasi-coherent sheaves on the cotangent bundle of bun G, and you can think about locsys for G check as having to do with kind of Higgs bundles for G check, so the cotangent bundle of bun G check. And there's a kind of old question that's out there: are quasi-coherent sheaves on these two spaces related to each other in some way? And what Braverman and Bezirkovnikov do is they say in characteristic P, D modules, well, there are known results towards this. So generically over the Hitchin base, this is a theorem of Tanavi and Pantev. For GM, it's just absolutely true on the nose. And there's a question which is like, how true is it as you specialize into the Hitchin base? I have no opinion about this, but Bezirkovnikov and Braverman say that in fact, D modules in characteristic P aren't so different from sheaves on these cotangent bundles. They're very, very close to the same thing. And they prove a version of that theorem, again, very generically on the Hitchin base. And so for me, it's just, yeah, so our theorem, I mean, it's a nice problem for someone to do, which is like, how compatible is this with, for instance, the Janagi-Pantev story? I'm not especially worried about that, which is something that makes sense purely in characteristic 0. And in characteristic P, and sometimes it would just be building on the same idea, I think. Yeah. Yeah, there's also an interesting story for big sheaves in characteristic P, but maybe that's for another time.
So you calculated the characteristic cycle of F sigma, and you said F sigma, the sum of F sigma rho. Can you calculate the characteristic cycle of F sigma rho?
I don't know what to. I definitely can't, and I don't even know what a good answer to that might look like. So if the centralizer, I mean, if the centralizer is trivial, then this decomposition I wrote is just in terms of the connected components. Yeah. Yeah.
Any other questions? Okay, if no questions, let's thank the speaker again.